on this example 6 is you're trying to find a recurrence relation and an explicit formula. Sometimes one is real easy and the other one's kind of challenging. So I'll show you kind of a strategy of how I figure this one out. Okay, now this one's pretty simple to see what's going on this. I mean, what's happening to each term? What are you doing? You're just cutting them in half, right? So the next terms on this would be 2, and then 1, and then 1/2, and then 1/2 of a half is a fourth, like that, okay? So if you look at that sequence, does it look like it's going to converge or diverge? Well, it's going to converge to 0 because it's just going to get a smaller and smaller denominator while the numerator stays to 1, okay? So if we do a recurrence relationship on this, what's really happened is we're just doing half of the previous term. And when you're doing a recurrence relation, you're looking at how it relates to the previous term like this, okay? So generally what you want to do is just write down what the first term is. Well, like we were doing last time, we use A as just what we're going to use to represent our sequence. So the first term is 64, okay? Then what you want to do is you write this as A sub n plus 1, and you relate that to the previous term, okay? The previous term being n, okay? So what are you doing? You're really just dividing it in half. So all you would do is write that like that, okay? And you want to understand how that recurrence relation works. It's just basically, if you look at this, like if you're looking at A sub 2, well, what are you really doing? You're doing A sub 1 plus 1, okay? If n is, when you're doing A sub 2, n is really the previous term. So what you would really be doing on that is you would be doing the previous term A1 over 2, and then A1 64, so you'd have 64 over 2. Okay, does that make sense? Okay, now it's easy to see the pattern on that, but you're always relating that to the previous term, okay? And that's what recurrence relations are. Sometimes those are easier to see than the explicit formula. Sometimes it's backwards though, okay? Now the explicit formula can be a little harder to figure out. I'm going to show you kind of how one strategy that might help you. Now sometimes you're going to see it, and it's going to be easy. I'm going to make a table, just try to make a little table in there somewhere. Didn't give you much space, so I'm going to write this kind of at the side. And we're just going to kind of make columns based on what n is, because when you're doing a explicit formula, what you're doing is you're relating everything back to n, okay? You're not relating it to the previous term, okay? So let's write down the terms. We have 64, we have 32, 16, and 8, and so forth. We'll take it out further if we need to, but we want to see if we have a pattern on that then, okay? So what's going on this thing then is we know that we're taking these things in half. Now what I'm going to do on this is kind of write what you're doing on here. This is what I see. That's 64 over 1. This is 64 over 2. This is 64 over 4. Yeah, okay, sorry. 64 over 8, and so forth, okay? Now see what I'm doing is, since I'm cutting it in half each time, that's why that's going up 2, 4, 8 like that. Okay, does that make sense? Okay, so by writing that out there, I'm beginning to see what the formula is. And I had to kind of just think about it and play with it a little bit. But the idea is if you cut something in half, then the second time you cut it, you divide it by 4. The next time you divide it by 8, and so forth. Okay, so let's think about what a formula would be on this then. So if you're doing this, now I think this one I wanted to look at, I wanted to write this like powers, like this. So this is really 64 over 2 to the second, 64 over 2 to the third, 64 over 2 to the first, and so forth like that. This is even 64 over 2 to the 0, okay? Now what I've done is I have figured out what that formula essentially is. So if you look at this, well, we know that 64 is always going to be in the 4. Now the bottom is always going to be what? It's going to be a power of 2. Now, how does that exponent relate to n? 1, 2, it's 1 less, right? Okay. Because see, when you're doing a formula, you're always trying to have n in your formula. So notice if n is 2, the exponent's 1. N is 3, the exponent is 2, and so forth, okay? So that means your explicit formula, you would write that of a sub n, okay, then it would be 64 over 2 to the n minus 1, okay? So that is your explicit formula on the problem. So that's a good approach, okay, that I think is helpful to me. It's probably helpful to you. If you struggle figuring out that explicit formula, try to write it out on a table and see if that helps you find the pattern. Does that make sense? Okay, because it's not going to be apparent all the time, okay? All right, so let's go to the limit of sequence. I am going to show you a couple of things here in a minute on how to use your calculator, which is pretty helpful when you're learning sequences. So when you're looking at the next thing is to kind of look at a limit of the sequence. We don't look at that very formally in this section. We look at it very informally, okay? So the idea with this is, this is a sequence, okay, that we're going from n equals 1 to infinity. What we're going to do is just make a conjecture about its limit. We're not going to get technical about that too much until the next section. Okay, so I'm going to show you how to put this in your calculator in just a minute, but what I've done is I went ahead and just crunched this out. So if n is 1, and I went ahead and just wrote this out so you can kind of see what I'm doing, you would have negative 1 over 2. If you go to the next one, you're going to have 1 over 5 and so forth. You can pretty well handle that in your head. We talked about this in the last class. What is that negative 1 to the n really doing? Change the signs, okay? That's how you alternate the signs, because what's happening is if n is odd, what do you get? A negative number. If n is even, what do you get? You get an even number. Does that make sense to everybody? Okay? So when you see that negative 1 to the n, that causes the signs in that sequence to alternate. So you see that all the time in sequences, okay? All right? So if you went through and graphed the points, now this is really how you do a graph of a sequence. It's not, it is a function. A sequence is a function, but it's not connected, but it would still, pass the vertical line test and everything. So it's a series of distinct points like that. So if you look at plotting those points, which is what I did, does it look like that's converging? Yeah, where's it going? Probably to 0. Okay, and if you look at your fraction, if you go through and just kind of list out the terms like this, well, you can see that the numerator is always 1. Although it alternates from negative 1 to 1, it doesn't matter. Okay, you're both basically still going to 0. So you would make the conjecture that the limit approaches 0 like that. Okay. Now, if you got your calculator, get your calculator out, because I was going to give you a handout. Boy, they're like getting all over us about copies. I was like, God, am I going to have to write the next test on the board? Maybe I'll just give you one integral or something. So, yeah. All right, we'll see. No, they're going to let us copy tests and everything. Oh, I'm being recorded right now. Oh, shoot. That's going to get out there on YouTube. I'm going to get fired now. That's okay. Okay. So no, that's fine. So anyway, you guys will back me up, right? Okay. All right. So in your calculator, let me show you kind of how to do this. You may have to write some notes to yourself. I will get you copies on that and everything. So the first thing is you want to press your mode button, and you haven't done this yet. What you've done so far, most of the time you're in function mode. So you want to identify that. Parametric, we will learn about that at the very end of the semester. Polar, if you took trig, a lot of you were in my trig class, we learned that just a little bit. But you see the one that says sequence at the end. So if you're going to graph sequences and put sequences in your calculator, you want the mode to go to sequence mode. So that's the first thing you want to make a note of then, okay? Now what we do is you're going to put the sequence in. So if you go to y equals, it'll look totally different now. Okay, notice everything's in terms of n, and you can work with a sequence of n plus 1, n plus 2. I'm going to leave that at sequence of n for what we're doing in here, because I'm doing a sub n. That's the way that's written then, okay? So basically what you do is n minimum is where you start. So if you look at this thing right here, n is starting at 1, okay? And that's typical, is unless it states otherwise, your sequence is going to begin at 1. Then you just put it in. So you just put in, like you would go -1 parentheses, then you'd raise that to the n power. When you use this variable key, that xt theta n, that's now going to be an n because you're in a sequence mode now, okay? Then you want to get out of that, you want to divide by n squared plus 1. It's real important you put the n squared plus 1 in a set of parentheses like that, okay? So you put that in just like you put a function. A sequence is a function, okay? But it's just going to be a series of discrete points when we do that then. Okay, now what you typically do is you put in the first two values, okay? So if you look at that, I already did this. I did -1/2, so I'm going to put in -1/2, okay, like that, okay? Then the second one is 1/5, like that. Sometimes you can just put in the formula there if you don't want to crunch those two things out. So it's going to want you to put in the first two terms of the sequence like that. Okay, everybody with me okay so far? Okay. What's that? Is it not asking? Okay, it may not. It may depend on the calculator. Okay, I have the TI 84 plus CE. Okay, that's why mine does it. Okay, now what we want to do is go to the window. Okay, and it may be on my calculator if I bypass that. Okay, so next thing is the window. Now the window, just kind of look at, what I did on my graph there. So we could go like n from 1 to 10. Okay, that's up to you. I'm just going to take n to 1 to 10. The plot start is at 1 and the plot steps at 1 like that. Okay, that's just where you start and you're incrementing by 1. You're going up 1. Okay, and the x minimum probably up to from 0 to 10. Okay, like that, like my graph is doing that I provided, and then increment by 1, and then the y values like this, they're decimals, they're going to 0. So the first term on this sequence I think was -1/2. So I'm just going to do something like, we can even do that if you want to, just -0.5, and then go to a max of 0.5, and then maybe increment that by 0.1 or something like that, okay? And then if you graph that, if you got everything put in, if you type graph, it should give those series of dots like that, okay? Now those of you who have different calculators, it may be slightly different, but now that I graph that, see, you get a series of points like that. So that's pretty cool. So you got sequences that you can graph, and that helps you to kind of visually see if it's diverging or converging, okay? Did everybody follow what I did on that okay? Okay, I'll give you a handout, I'll try to do that next week. You can also Google or YouTube and say how to put a sequence in a TI, and you'll probably get a nice video on that, okay? All right, so we're going to do that calculator a little bit as we go through. I just wanted to introduce you to that idea. Okay, so next thing I want to do, and I think on your handout I printed all this stuff out on the next page, isn't that right? And just to kind of help you, so if you didn't get all that written down, don't worry about it. It's all there for you, thanks to your teacher, okay? So there's your graph. That's how I set up my window. That's how I put that in, okay? All right, so let's go on to the next thing. Mainly what we're going to do is just look at sequences, write out terms, do a graph, and make a conjecture. The conjecture is just not formal, but it's visualizing if this sequence is going to converge or diverge. And there's different things can happen. So this sequence, we're doing the cosine of n pi, and we're going from n equals 1 to infinity. Okay, so we're going to list out the first 4 terms. So to start with this, we're going to have cosine of 1 pi. And then we're just going to vary the n. So we're going to do cosine of 2 pi, cosine of 3 pi, and so forth like that. All right? So we want to do that. I got a unit circle on here. I mean, you don't really need to look at the unit circle. I mean, you just need to look at those key points on there. Okay, so what's the cosine of 1 pi? -1. Okay, so we got that. All right, what's the cosine of 2 pi? What? 0. Okay, cosine of 2 pi? 1. Okay, sine. Okay, you might be thinking of sine there. Okay, so that's 1. Okay. Cosine of 3 pi, back to -1. Cosine of 4 pi, back to 1. Okay, do you see what's happening? Okay, it's alternating because remember, this is one pi is like that, okay? If you go around again, that's 3 pi. And then you would have 5 pi and 7 pi. Over here, that's an odd pi, right? Okay, and here, like this would be 0 pi, 2 pi, 4 pi, that's even pi. Does that make sense to everybody? Okay, so like in my trig class, I gave this problem on a test. What's the cosine of 88 pi? Students freaked out. Okay, what is the cosine of 88 pi? Okay, because it's an even pi. Okay, so I had students taking their calculator, 88 times 180, and doing stuff like that. Okay, I'm not criticizing that. I mean, it's what you do in math is you look for patterns. So there's a pattern to that. Okay, that's the idea. Okay, so then if you went through and if you graphed this, you would have at n equals 1, you would be down at -1, so you just put a dot there. A sub 2 would be up 1. A sub 3 would be -1, and 4 like that. So it would do that forever. So would that converge or diverge? Okay, because they're not going to the same place. Now, you know, the upper one is always going to be 1 and the lower one's 1. So you're going to say that this sequence basically diverges. Okay, so that's something that can happen is you just have an alternating sequence like that and they don't go to the same point like the previous problem did. Okay, and then that one could be put in your calculator. I'm not going to do that on every problem, but I want you to know how to do that. Okay, let's look at the next one. Now this one is given in what's called a recurrence relation. So the last two problems I had given you the explicit formula. So this is a explicit formula, so let's go ahead and work that out. All right, so what I've done on this, now sometimes, I did one of these in the when we did the Fibonacci sequence. We can start at A0 if we want to, and a lot of times, like in physics or something, we use A naught to represent the initial something, okay? So we got that, that's our first one. Now if we're finding A1, we need to do what it tells us to do. So if you're doing A1, you are doing 1 minus the previous term, which is 2/3 over 3. So you want to work out that math when you do that then. Oh, it's over 2, okay. All right, so we want to do that and just kind of crunch that out. Okay, so that's over 2. So that's going to be 1 minus 2/3, and if you're dividing by 2, you're just multiplying by 1/2, like that, okay? So that would end up being 1 minus 1/3, so that's going to end up being 2/3. Interesting, it just turned out to be the same thing, okay? Let's go into A2 and see what happens. Okay, now if you do A2, think about what you're doing. Well, you're going to this recurrence relation formula, so you're doing 1 minus the previous term, which is 2/3 over 2. Didn't I just do that math problem? Okay, so I don't think I need to do it again, right? So what's the answer? 2/3. Is it ever going to change? What? You think I should keep going for the rest of the class? Okay, to convince you? Okay, all right. No, you're going to keep doing the same math problem, so it's going to keep being 2/3, okay? All right, so I mean, if you see that, and that does happen on a sequence, you can have sequences that just create a constant term. That's an example of that, okay? So of course, if you graphed this, then it would just be, you know, you just kind of put a couple of dots on here. You could do this like this. This is 1, that's 1/3, that's 2/3, and so forth like that, okay? So it's just a constant. N is 1, you got 2/3, even A sub 0 was given as 2/3, so it just goes like that, okay? And that's the idea. Okay, so that one does converge, okay? It converges to 2/3. So that would mean we would say that the limit as n goes to infinity of this series, of this sequence, is just going to be equal to 1, like that, okay? And I'm just writing A sub n as the sequence, okay? The fact that I gave A sub n plus 1, that's a recurrence relation, so that's what the limit is. That's how you write that, okay? So see, that's a couple of different examples. You can alternate like we did on the previous example, or you can be constant, okay? All right, any questions? Oh, no. What did we say? It goes to 2/3, not 1. I don't know why I'm thinking 1, so 2/3, okay? All right, so let's go to the next one. I want to do a few more things like that. And then we're going to transition a little bit into a little bit more technology here in just a minute. Okay, so again, this one is given, this is an explicit formula this time, okay? So you're just doing, n starts at 1, so we're going to start this first one. We're really doing 1 minus 10 to the negative 1, okay? So we're just going to plug that in. So what that's going to be is that's 1 minus 1/10, okay? So that is 10 tenths minus 1/10. So that's going to be 9/10, okay? And you could write that as a decimal. That will maybe kind of help you see what we're going to see in this problem as we do this. Okay, then I go to the next one. The next one is 1 minus 10 to the negative 2. So that's going to be 1 minus 1 over 10 to the second. That's really 1 over 100. So, and you can do this in your head. Whatever you can do in your head is fine with me on this. So you're just doing 100 over 100 minus 1 over 100. So that's 99 over 100, okay? So that's 0.99. You divide by 100, the decimal moves back 2 like that. Now you can already see what the pattern's doing, okay? And once you see the pattern, you don't necessarily have to do the rest of the arithmetic. I'll do it one more time. So that's 1 minus 1 over 10 to the third. 10 to the third is 1,000, so I'm going to get a common denominator, write that as 1,000 over 1,000 minus 1 over 1,000. So that's going to be 999 over 1,000. So that's 0.99 like that then. Okay, so you can now tell what the next one's going to be. The next one's going to be 9,999 over 10,000, which is going to be 0.999 like that. Okay, so that's how that one's going to go. Okay, does that make sense? That's mainly just arithmetic is what you're doing. Now, what we're going to try to do on this is what we're interested in is the limit of this sequence as n goes to infinity. We're doing the sequence 1 minus, and I'm going to write that as 1 minus 1 over 10, like that, okay? Now, conjecture, where's it going? 1, yeah, you're okay. That's going to 1. You can tell by that it does that then. Now, when we start getting a little bit more into the next section, we start doing this more analytically. And you know, you already learned how to do that in Calc 1. You really did. Okay, if you look at this, what's the limit of 1? 1. What's the limit of 1 over 10 to the n if n is infinitely big? That's 0, because if you have 1 over infinity, that goes to 0. So see, a lot of this stuff will relate back to what you did in Calc 1. You'll even start using L'Hopital's rule again on these sequences, okay? It'll happen. You excited? Okay, all right, we'll get back to L'Hopital, and we'll actually review that a little bit today. Okay, so that's how that goes. Graphing the sequence, you don't really need to do that. I mean, you can. It's really what's going on this is you've got 1, 2, 3, 4, you got 1 here. I mean, your dots are just, you know, getting towards 1, okay? That's not all that important, okay? You kind of use the graph if you, sometimes if you're having trouble seeing how that sequence converges or diverges, but it's a good tool. Okay, so let's see. Let's do this one. I want to kind of finish up the sequences, then we're going to look a little bit at series. So this one is one that I'd like you to put this in your calculator just one more time, just to make sure everybody knows how to do that. So I've kind of written on your handout everything on here. I'd just like you to put that in one more time. So if you didn't catch it the first time, and you just can put it in exactly the way it is. I'm going to put in 2, and then I'm going to put in inverse tangent of 1,000 n. And you got to be, of course, in your sequence mode like I showed you. You got to do that first. Okay, so you want to get that in. You want to be in radian mode on this now. So, you know, if you're in degree mode, you aren't going to get the sequence that I'm looking for. So make sure that you're in radian mode like you did in trig. And remember your mode on this is you want to go, you're in sequence mode now. So you got to learn how to go back and forth on that. Then the window, let's see, 1 to 10, be pretty similar to the last problem. I think the only thing is I wanted to change the y values a little bit on this one. So, and it has to do with pi. That's what I want you to see. So you make your y window go 0 to 4. by a scale of 1 like that, okay? And then if you got your window set up, there's a couple of other tools you can use to analyze whether it diverges or converges. So when you put that in, and if you got everything in like I've got here, you're going to kind of get just a series of dots like that. And what happens is they're converging to some value like that. I have kind of a weird dot there. I'll make sure I put that in right there. So I think I got everything okay. Did I miss something? Oh, I have those things wrong. Yeah, those things are way wrong. Okay. I think I can leave those things off. Let me try that. I think on this calculator I can leave those off. Okay, there we go. Okay. All right. So with this then, you can tell it's converging. But one thing that kind of helps you on this one is, I was just going to show you your table. So if you go second graph and open up your table, that's another good way to analyze whether the sequence is going to converge or diverge. It's pretty clear that it's going to pi, right? Okay. And you're dealing with an inverse tangent, so there's a good chance there's a pi involved like that. So you would conjecture based on your technology on this one that one is basically approaching pi. That's what I wanted to show you on that one. Okay. And we'll get to a point a little later where we'll do that analytically, but that one would be a good one to just kind of look at with technology. Okay. What's that? You have an error? Oh, yeah. Okay, now that may end up being, if you go back to right here, okay, the reason that that's happening on this is, number one, your sequence was defined to start at 1, okay? So it's still going through and doing those calculations like that, okay? You still, on an inverse tangent also, one thing you got to remember about an inverse tangent, there's a range to it also. Okay, an inverse tangent's defined to be from a range from negative pi over 2 to pi over 2. Okay, so you've got that involved, but what's happening on that, if you do like, these all right here are basically giving that because you started your sequence at 1. That's the only reason, okay? Okay, all right, now let's do this problem with the bouncing ball. This is just sort of a physics thing here, and this is kind of how sequences work. You could think of a bouncing ball as a sequence. So, you know, the idea is you got a basketball, you drop it, and it bounces. The height is always changing, isn't it? Okay, the first bounce is the highest, and then it's going to be lower and lower and lower and lower. So it's going to look like that. I took that example out of the book. That's a pretty good example for sequences, and applying that in some context, you can look at it like that. So those heights are getting smaller at some rate. Now, obviously, it has to converge to a height of 0, right? Okay, or the laws of physics are being violated, right? Okay, it's got to hit ground at some point in time. Okay, this is kind of a nice example on this. So the idea with this would be, what they say is each time the ball bounces on the floor, it rebounds to 0.8 of its previous height, okay? And again, that's sort of giving you a recurrence relationship, and then it's giving you the initial height is 20 feet. So this time they've given you initial like this, and then we're going to crunch these things out like this. So what you basically do, according to this problem, is on the second bounce, you're just doing 0.8 times 20, and then you're just working that out, okay, which I think that's what, 16, okay? And you'll start getting into some decimals and stuff on this. Now, what I'm going to do on this is I'm going to write this a little bit different way. I mean, you could go through, let's do it this way first of all, 0.8 times 16, and you can work that out. Some of these I've already worked out on the calculator, so I don't want to take the time to do that. That's 12.8. Then if you did like 80% of 12.8, that's going to give 10.24, and then if I do 0.8 of 10.24, that's going to be 8.192. So obviously it's heading towards 0. It's going to take a lot of bounces to get there, but eventually you would end up getting there. The mathematics wouldn't imply that, okay, but you're eventually going to come to rest. Okay, so the recurrence relation on this goes like this. What you want to do is, the first thing is you were given that the initial height was 20, and when you're doing a recurrence relation, you're defining the next term in terms of the previous term. So what would that be? What did we just do over and over again? We did 0.8 times the previous term, right? Okay. You can think of this as your h of n, okay? To get the next term, you did 0.8 of the previous term. So you write this like this, you would say 0.8 times, and then we're using h this time, so we would say h sub n like that. So that's your recurrence relation like that, okay? That's what the problem is saying. Does that make sense? Okay, now the explicit formula is usually a little harder, and if I write it this way, you'll see it, okay? So I'm going to just kind of write a table. You don't have to do this unless you're having trouble seeing this, okay? So I'm going to just write out a couple of terms, and then once you see the pattern on this, you'll begin to get this. This is an approach that's useful if you need to do this, okay? So first of all, really at n equals 0, and n sub 0, we know that's 20, okay? Well, what we did to get the h of 1 is we did 20 times 0.8, okay, like that. That's what we did. Now, I'm going to write this a different way. When we go to the next term, you know what we did? We did 0.8 of the previous term, but instead of multiplying that out, I'm going to write it this way. I'm going to write that as 0.8 times 20 like that. That's what we did, right? Okay, we just crunched out 0.80 times 20. Now let's go one more time, and I think you'll see the pattern. When you go to the next one, what you're going to do is you're going to do 0.8 times the previous term. But the previous term, let's not bother multiplying it out. Let's do it that way. Write it as 0.8 times 0.8 times 20 like that. Okay? Are you beginning to see the pattern now? Okay? See what you're doing on this is you're doing 0.8. That'll be 0.8 to the second. That'll be 0.8 to the third. And you always have a 20 in there. Now that's called a geometric sequence, which is something that we're going to learn about. So basically this is going to go like this. When you put together your explicit formula, you know that you always have a 20 in there. Okay, there's no doubt about that. Okay, and it's all about relating to n. So this thing right here is really 0.8 to the first. This is 0.8 to the second. That's 0.8 to the third like that. Okay, so how does that exponent relate to n? The same, okay? So what you'd end up having is you would have times 0.8 to the n power, like that. The first one even works, okay? This one, see, would be 20 times 0.8 to the 0. Wouldn't that be 20? Okay, so it works, okay? So typically when you have, that's what we call a geometric sequence, and geometric sequences are always, you're always multiplying the previous term by something, by some factor. And geometric sequences, we're going to learn, always have this structure, something to a power, and then some number in front like that multiplied. That's a geometric sequence. Okay, does that make sense? Okay, now the benefit of that is, well, we could find the height of the ball after the 10th bounce. Because all we got to do is plug into that explicit formula. So if we do the 10th bounce, all we're going to do is we're just going to do 20 times 0.8 to the 10th power, and then you can do that on your calculator. I don't know if I did that or not. I may have. Yeah, I could have that. You can do that if you want to and check this. I got 2.147, okay? And then if you want to do the 20th bounce, you just do 20 times 0.8 to the 20th power. And then if you type that in, you're going to get 0.231 like that, okay? So see, that's the benefit of that, is you can just immediately crunch that out with one formula. Yes?
So what's the point of the recurrence relationship? You have to know the previous term, so you have to go through a whole list.
Well, it's two ways of writing a sequence, and they can be written in different ways. Sometimes one way is a lot harder than the other. Like, for instance, the Fibonacci sequence that we did the other day, that one is best written with a recurrence relation. Okay, just kind of depends on the situation. Okay, so there's two ways to do that. Okay, well, that should make sense. Obviously, it's going to 0. So your idea would be the limit would be going to 0. I did this on the graphing calculator, and what that's showing is, you know, the height of each thing. Okay, now if you did the mathematics on this, the mathematics will never get to 0, right? Okay, but the limit will. Okay, so that's kind of the idea. You can use that to model that kind of an idea. It's not perfect because in physics there's lots of other things to consider, friction, all kinds of things. So that's just kind of an idealized situation. Okay, does that make sense to everybody? Okay, right, so that's what we call a geometric sequence. Okay, now we're going to move to series. And because we're going to be studying series and everything for the next few weeks, and one thing that you want to get down is the difference between a sequence and a series. Now, a sequence is a list of numbers, right? That's all it is. It's a list of numbers, generally with some sort of a pattern that we could relate, maybe in a recurrence relation or explicit formula. What an infinite series is it's a sum of an infinite set of numbers. So you're now adding a bunch of numbers is what you're doing. So an example, typically what we do in a series is you just write it kind of like that, a sub 1, a sub 2, and so forth like that. So you're really adding up terms in a sequence, okay? So this would be an infinite series. A half plus a fourth plus an eighth, plus a 16th, and so forth. We're going to look at that one right there. That's a good starting example. This is the example they have in the book, and it's a very good example because visually it helps you kind of understand that. So the idea is if you sum an infinite number of numbers, it's possible that you can get a finite answer because of the limit, okay? That's bizarre, but that's what calculus kind of solves is that problem. You go back, a couple of thousand years, that would just be nonsense. That's impossible. But no, you can add up an infinite number of numbers and get a finite answer because it can converge or it can diverge. Sometimes it doesn't. Okay, so we've talked enough about that. Hopefully you're kind of beginning to wrap your brain around that a little bit. It's a heavy thought, but it works beautifully with calculus. So the idea with this one is what they've done is visually they kept cutting this in half. So like if you look at this particular square right here, you could think of the area of this square, of course, would just be 1, okay, because 1 times 1 is 1. What they're doing is they're cutting it in half over and over again like this sequence is doing. This sequence, all you're doing is you're just cutting each fraction in half each time. And if you get all the way down to it, well, what's happening to the size of those squares? They're just going infinitely small. So the idea would be on this one is if you added up this infinite series here, it should go to a value of 1. Okay, and that's because you're really just kind of taking the square and dividing it up infinitely, but now if you put it back together, all of those tiny squares are going to add back up to the original, right? Does that make sense? Okay, so that's a good way to explain how a sequence or a series could converge just by looking at a picture, okay? So that's a good starting point. Now what we're going to learn how to do is look how to analyze these with calculus. In this section, primarily, it's just very informal, kind of like when you're in Calc 1, you learn about limits very informally first before you get formal with it. Okay, so this one right here, I've given on this one a series, okay, and what we're going to do on this is write out the sequence of partial sums. I need to explain what that is. And then we'll make a conjecture about that. So when we make this into a sequence, one of the things you do with a series is you can turn it into a sequence of partial sums. Now here's what I mean by this. It's actually a fairly simple thing. Okay, S of 1 would just be whatever you start with. Okay, and that's 0.3. S of 2 is just going to mean we're going to take the first 2 terms and we're going to add them together. Okay, that gives what we call a partial sum. That's not a sum of the whole series. It's only a sum of the first 2 terms. So what's that? 0.33. Okay, like that. Then when we go to S of 3, what you're going to do is you're going to add the first 3 terms of that infinite series. Okay, when you do that, you're going to have 0.333 like that. You guys see what I'm doing? Okay, that's called a sequence of partial sums. When you go to the next one, you can tell what you're going to get. You're going to get 0.333 like that. Now see, what you've done is you've turned that infinite series into a sequence of sums, right? So remember when we were doing sequences, what we've been working on, is you're just sort of seeing where this sequence goes. So you have 0.3, 0.33, Where's it going? A third, exactly. Okay, you got repeating threes. Okay, all that's going to happen is you're just going to get more and more decimals of repeating threes. So you can conjecture on this problem then that the limit of this series would be the same thing as the limit of the sequence of these partial sums. So I'm going to write that as the limit of S of n, standing for the partial sums. That's going to approach 1/3 like that then. Okay. So that's the idea. So that's the approach we're going to take for now, is to look at these things as partial sums. Okay, yes? You're talking about the one with the squares? Yeah, that's the one for the squares. I mean, they all add up to the square. Okay. Nope, that's not it. Now, I'm going to show you how this formula, where this formula comes from here in a minute. Okay? All right. So let's do this next one, kind of the same idea. So again, what you do is S1 would be the first term. What you're going to do is you're going to do partial sums. So when you're doing this, when we do S2, that's just going to be 1 plus a half. So that's 1 1/2. So that would end up being 3/2. Okay, and we're going to see if we see some sort of a pattern to it. We may or we may not. We go to S3. S3 is going to be, and you can do it like this. This is the best way to do it. Just do it like this. Just take the answer to the previous thing, because we've already added up the first two terms. So we've already got 3/2. Add on the third term, 1/4 like that. Okay, so if you got a common denominator, that would end up being 6/4 plus 1/4. Anything you can do in your head's okay. You know, just do that. That's 7/4. When we go to S of 4, we can take the previous sum, 7/4, and then we can add the fourth term to it, 1/8 like that. Okay, so if I got a common denominator, the 7/4 would become 14/4. Then we'd have the 14/8, sorry. Okay. So yeah, we'd have 14/8, and then you'd have plus 1/8. So you would end up having 15/8 like that. Okay, now remember what these are doing is these are sums. Does that make sense? That what I mean by partial sums? Okay, now see what we do is we have a sequence, and that sequence is just summing more and more terms. So if that sequence converges, that should be where the series converges to. So does that look like it's going anywhere? It's going to 2, yeah. And if you look at the pattern on this, what's the pattern on the denominators? 2, 4, 8. Those are powers of 2. That shows up a lot. I mean, we see that a lot. How about the numerator? Do you see what's happening on the numerator? That's a little harder to see, but there's something going on there. Yes, okay. And what's happened? I look at it like this. This is 1 less than 4. That's 1 less than 8. That's 1 less than 16. Okay? So see, that's really 1 less than 2 to the second. That's 1 less than 2 to the third, and so forth. So what's going to happen on that is if you wrote an explicit formula for this, you would have 2 to the n minus 1 over 2 to the n minus 1. Okay? Now, I'm not worried about that so far now. You just want to be able to list and see where that sequence goes. Okay, so what we would say is the limit of n goes to infinity of the partial sum sequence. Now, remember, that's a sequence. Okay, we're changing the series into a sequence. So that's going to go to 2. Okay, all right? So you're always going to have that kind of situation. Okay? All right, does that make sense? What we mean by partial sums. Okay, that's one approach to figuring out whether an infinite series converges or diverges. Okay, so on the next page, this is a little bit more formally defining things. It's still not real formal, but we're getting there. Okay, so what we say is if you have a sequence and the sum of its terms, okay, this is a infinite series. So you probably remember back from Calc 1, when you were doing Riemann sums, you use that sigma notation a lot. So if you've ever taken statistics, you see sigma everywhere in statistical formulas. All that does is that stands for sum, okay? And that's summing discrete terms. Of course, in calculus, the sigma turns into an integral when you start working with functions. and working with that. So they're really doing the same thing, except this is summing up a discrete number. So you're going from k to infinity. What that is, again, is it's a sum of terms. Okay, so you want to make sure you have this down. What's the difference between a sequence and a series? Sequence is a list, right? What's a series? It's a sum, okay? So you want to get that in mind. Very simple, you want to have that down, okay? So now what we do is we write this as a sequence of partial sums, like I just showed. That's what that's doing, is it's summing up the terms. That's summing up 3 terms, 2 terms. Eventually, it's summing up n terms. So what it's saying is, if you were to add up those sums, those partial sums, you should get what the value of that infinite series is when you add it up. Okay, now it can diverge. Okay, we'll see some of that. And then the other thing we say is, this right here is showing, we're looking at this series, that's a series, okay? So it's saying this is really going to be the limit as k equals 1 to n, like that. And what we're doing is, if you think about this, this sort of relates to an improper integral, kind of in a way. When we did an improper integral 1 to infinity, what did we do? We changed that to like a b, and we took the limit as n goes to infinity. It's essentially doing what an improper integral does. So that just says that's going to be the limit of s. S is the sequence of partial sums, and that should be the value of the limit. That's not real formal, but in mathematical terms, that's what I just did on the last 2 examples. Okay, does that make any sense? Okay, so we're turning the series into a sequence of partial sums. That's the idea. Okay? All right, so let's do a few more things with this. With this one, now this is an infinite series. Now see, I've written that in the form with the sigma notation like that. So let's go ahead and let's just write out what a couple of terms like this, what this is doing. Before we do the sequence of partial sums, let's write out some terms. So what we'd have is, this would be 1 over 2 to the first, plus 1 over 2 to the second, 1 over 2 to the third, and then you're going to go on forever, and eventually you'll have 1 over 2 to the k. Okay, k is the variable. We call this thing the counter. Okay, so that's just going up by integers like that. So that's what the series is saying, is you're adding up an infinite number of numbers. Okay, either it will diverge or it will converge. Okay, that's what we're going to try to figure out. So when we're doing partial sums, S1, what is S1? It's the first term. Okay, it's a half. Okay, then when you go to S2, what are you doing? You're doing a half plus a fourth, really, right? You're just adding those first 2 terms. So that's going to be 2/4 plus 1/4. So that's going to 3/4, like that. Okay, now when you go to S3, just do it this way. Just take the previous sum and then add the third term, which is going to be 1 over 8, like that. Okay, get a common denominator. You can change 3/4 to 6/8. 6/8 plus 1/8 is 7/8, like that. Now I'm going to do it one more time, and then ultimately we're going to try to look for a pattern of that sequence. Okay, now you would take 7/8 and you would add the next term, which would be 1 over 16, because it'd be 1 over 2 to the fourth. Okay, so that would give you, with a common denominator, 14 over 8. No, I keep doing that same mistake. Okay, I know what I'm doing though. So that would be, I think, 14 over 16 plus 1 over 16, so it's 15 over 16, okay? All right, that's your partial sums. Does everybody understand what I'm doing there? Okay, it's arithmetic. Okay, now what we're going to do, if you just look at that sequence, does it look like it's diverging or converging? It looks like it's converging to what? That's what it looks like, okay? We're going to be a little bit more formal with it this time, though, because this time we want to find a formula, okay? So the idea is, when you look at this formula, I'm going to kind of write this at the side right here. You do have a pattern here. You have 2 to the first. The denominator is easy to see. 2 to the second, 2 to the third, 2 to the fourth. Okay, that's easy to see. All right. Now, the numerator sometimes is harder for students to see. I did this on the last problem, but these are just 1 less than perfect squares, right? That's 1 less than 4. That's a perfect square. That's 1 less than 8. That's a perfect cube. That's 1 less than 16. Okay, like that. So when you put that together, your formula would go like this. Okay, we'd say for the sequence we would have, and we're going to write an explicit formula. The denominator, what does it look like the denominator is going to be? Okay, 2 to the n, right, okay. S of 3, you have 2 to the third. S of 4, you have 2 to the fourth. So that matches the n, so that's going to be 2 to the n. Okay, now the numerator is going to be 1 less than a power of 2. So if you look at this right here, that's 1 less than 2 to the fourth, right? That's 1 less than 2 to the third. So what you say is you say 2 to the n, and then you got to put the minus 1 out of the exponent, okay? Now, whenever you come up with a formula, it makes a lot of sense to just make sure you're right. I mean, if you plug something in, let me just say n's 1. Let's see if n is 1 gives you 1/2. So if n's 1, you would have 2 to the first minus 1 over 2 to the first. Okay, that's 2 minus 1 over 2. That's 1/2. So it works. And if you do that a couple of times, then you're going to know that you're on the right track with that. Yes?
Is there always like a correct answer? Because the way I'm looking at it is probably really random, but it's like adding half and multiplying.
There is more than one way to write that. Mathematically equivalent, there's several ways to write that formula. Okay? Now that's what I see. There's other ways. What did you come up with something different?
Well, I don't know how you write it, but you're taking the numerator and then adding a half and multiplying by 2.
Okay, that might, if you wrote that down and formalized it and worked it out, you may end up having the same I have. I wouldn't know unless I worked that out and wrote it down. But what you do a lot of times on these problems, you look for powers. Powers show up in these things quite a bit. Okay? All right, now let's do this. So what we're going to do now is we're going to do the limit as n goes to infinity of the sequence of partial sums. So let's write it like this. We're really going to do the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. Now we can do this limit now. I mean, we know it's going to go to 1. We can pretty well tell that, but you learned how to do this in Calculus 1, okay? What you can do on this is you can break that limit up, you can break that fraction up into 2 parts. Okay, so let's do this like this. Let's do the limit as n goes to infinity of 2 to the n over 2 to the n minus 1 over 2 to the n like that, okay? And I'll write one more step because I want to write it kind of, pretty formally. So that's going to be 1 minus 1 over 2 to the n like that then, okay? All right, so remember that the limit of a sum is the sum of the limit. So what's the limit of 1? 1. What's the limit of 1 over 2 to the n? 0. Because that just makes that 1 over infinity, right? 1 over infinity is approaching 0, so this thing just stays 1. That thing right there goes to 0 because that's really 1 over an infinitely big number. So you get 1 plus 0, you get 1. So that's more formally how you would do that limit. Yes? Oh, minus, yeah, okay. I'm lucky that it got the same answer. Okay, yeah, you're right. I do that sometimes. No, you're good. You're good. That should have been a minus, but like I said, blind luck, I got the right answer. Okay? All right, yes?
Can you teach us how to use sigma in calculator?
For what purpose are you thinking about? Just doing a sum or?
For example, for those formulas to find the area of the curve approximated, instead of going through those.
I'll tell you one thing I know. I don't want to take too much time on that, but I can show you one thing I know, okay? If you go to if you're just asking how would I sum up a bunch of stuff, right? Okay. What you can do is you can go to the Stat button, and then when it says Edit, you just enter a list. You can enter a list of numbers if that's what you're asking about, okay? Now formula-wise, if there's a formula, I'm not sure that I know how to do that. But if you wanted to just add up a list, now see, I've already got a list in there, okay? If you go to back to Stat, and then you go to Stat Calc, there's a thing called one variable stats, and it will do some different sums for you. This is just what I know. There's probably some things on there that I'm not aware of. But if you look at that, see what that said, sigma of x? that summed up all those numbers for you, okay? And then sigma x squared, that's something you do in statistics. So I know that. That's about the extent of how I could answer your question today. There may be something else, though, that I don't know about, okay?
Yeah, these formulas
It's like using the same point formula and stuff.
If you enter the data into a stat list and do that one variable stats, it'll do it for you. That's what I know. There may be another way to do that, okay? All right, so let's go to the next page here. And let's go ahead and look at this one. Just kind of the same idea. So I want to go ahead and finish up this this last page here. Then we'll do our break. Okay. So, right. So this time, let's go ahead and let's write out some of the terms. So k is 1. So we would have 1 over 4 times 1 to the second minus 1. Then it's a series, so you're plus, and that would be 1 over 4 times 2 to the second minus 1. And then 1 over 4 times 2 to the third minus 1. And I'll do that one more time because we're going to do the partial sums like that. Now, little things like this, you can do some of these things on your calculator if you want to. Oh, yeah, okay. I'm starting to count something that doesn't exist. Yeah, it's always to the second power. Okay, what's changing is the k. So, yeah, that would be always to the second power like that then, okay? All right, well, let's just work out the denominator. You can probably do all the denominators in your head. So that's going to be 4 minus 1. That looks like a third. The next one is 4 times 4 is 16. 16 minus 1 is 15. Okay, then the next one, 4 times, no, that needs to go up 3. See, I'm messing up with my counter. I did that fast, and that's what happens when you do stuff fast. Okay, let me rewrite that a little bit better, and you guys can work on it while I'm doing that. So you got 2 to the third minus 1. Then the next one is 1 over 4. See, I'm making the same mistake. Oh, that's really bad. 3, now I think I've got it under control, but I got to change that. Okay, here's how you can avoid that mistake. Okay, you do this. You do 1 over 4 to the something squared minus 1 plus 1 over 4 times the something squared minus 1. Okay, all right, now what's happening? It's this that's changing. Am I good now? Hallelujah, okay. Okay, so the next one is, let's see, 9 times 4 is 36, minus 1 would be 35. The next one would be 16 times 4, 64 minus 1 would be 63, like that. Now see, as I'm doing that, I'm already kind of seeing a pattern on that. So again, what we're doing is partial sums, okay? So what's S1? A third, okay? The next one, you're going to do 1/3 plus 1/15, so you're going to get a common denominator. Now, if you're in a crunch, you're doing your homework and stuff, you can use your calculator and do that math fraction things. Everybody know how to do that, okay? Okay, so this is, that's going to be 5 over 15 plus 1 over 15, like that. So that's 6 over 15. I'm going to leave it in an unreduced form because I might see a pattern a little bit better on that. Okay, then the next one you're going to have is 6/15. The previous term plus the next term. The third term is 1 over 35. You know what? I probably should reduce it now that I think of it because I'll see it easier. So let's take this one. That one was 6 over 15. And then if you divide that by 3, you'll have 2 over 5. Okay, I was thinking I might see the pattern better, but I think not. Now that I think it's better just to reduce this. Okay, so when we go to the next one, what we want to do is do the 2/5 plus the third term, 1 over 35. Okay, get a common denominator, so that's going to be 14 over 35 plus 1 over 35. So that's 15 over 35, like that. Okay. Right, and that reduces. I need to reduce that too. Okay, so let's see, 15 over 35, you can divide by 5, so that gives 3 over 7. Okay, now I'm seeing a pattern. Okay, once I see a pattern, then I don't have to do the arithmetic. What's the next one going to be based on the pattern? Yeah, 4 over 9, right? Okay, because it looks like the numerator is just going 1, 2, 3, and the denominator is going 3, 5, 7. It's going odd numbers like that, okay? So then what you should get on that is you would have 4 over 9 like that, okay? So what we want to kind of look at is we're going to look at a formula basically for this, and in order to figure out what the value of the infinite series is, okay? So let's see, if you look at this, okay, what's the numerator? What would the numerator be in your formula? It'd be n, exactly, because that is what it is, okay? 1, 2, 3, 4, okay? So your formula, you're definitely going to have a n in the numerator there. Now, what's happening on this one is these are odd numbers, okay? Now, there's one thing that you may or may not know that's really helpful to know is if you have an even number, a formula for that you can use is 2n, okay? I mean, because what happens if you double any number? Don't you just get an even? 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. So that's a formula for an even number. Well, what do you think a formula for an odd number would be? It's just 1 bigger than that, right? Okay, so that's worth writing down because you're going to use that a lot. So evens are written as 2n, odds are 2n plus 1. Okay, so let's see if that 2n plus 1 would work on this, okay? Well, if n is 1, then what would the denominator be? No, 3, okay, you're thinking of the wrong thing, okay? So it would be 3, so it seems to work, okay? That's given the first odd number like that, okay? So that would be your general formula. You have n, and then you have the odd number in the bottom, okay? Does that make sense to everybody? Okay, all right, so what we're going to do is we're going to now do the limit. So we're going to do the limit of the sequence of partial sums as n goes to infinity. So that's going to be the limit as n goes to infinity of n over 2n plus 1 like that then, okay? Now, when you're looking at this one, this again is something you learned how to do in Calc 1. One way to do this limit mathematically, there's a couple of things that you may remember. One way to do this is to divide, and I'm going to do it this way to start with, is to divide the highest power of n is 1. So what I'm going to have you do is do it this way for now. Let's divide every term that you see in this problem by n. This is one way you would have learned how to do this. There's other ways you learn too, probably. Okay, so let's do this like this, and then let's see what we end up with, and then we'll reevaluate the limit. Okay, so what you're going to have is you're going to have the limit as n goes to infinity of 1 over 2 plus 1 over n like that. Okay, now without using all the limit laws, I like always tell students that the limit laws are why you can do this. You can really do the limit of the numerator, and then you can do the limit of 2, and then you can add to that the limit of 1 over n. So what you have on this then is the only thing you're going to look at is this thing right here. Where is that thing going? That's going to 0. So what you have is 1 over 2 plus 0. So we got 1/2. And if you look at the numbers we were coming up with, that makes a lot of sense. Okay, so that sequence is going to head there, but that's mathematically how you would do that. Okay, does that make sense to everybody? Okay, all right. Okay, the other way that you would have learned how to do this problem, I'm just going to mention this real quick because we're going to review this in the next section anyway. So if you were doing the limit as n goes to 0 over n over 2n plus 1, okay, the numerator is going to infinity. The denominators also go to infinity. So that's what we call an infinity over infinity limit. So you can use what's called L'Hopital's rule, which you remember, right? Okay, what does L'Hopital's rule tell you to do? Take the derivative of the numerator and denominator, then reevaluate. So here's what you could do. If you were doing L'Hopital's rule, the derivative of n is 1. The derivative of 2n plus 1 is 2. Okay, then you do the limit of 1/2 and you got 1/2. L'Hopital's rule is going to come in handy in this chapter. We're going to get back to doing it. Okay, all right, let's do this last problem and then we'll take a break here. Okay, so this one, the key thing is you want to get to a point where you see this. What do you think that -1 to the k is going to do? It causes it to alternate. That's what makes it an alternating series, okay? So let's write out the terms. So we'll have, and I'm going to be careful this time, -1 to the k times k. So it's going to be -1 to the 1 times 1 plus -1 to the 2 times 2 plus -1 to the 3 times 3. And I'll do one more term, that's -1 to the 4th times 4. Okay, so let's do that. Okay, this is all, you can do this in your head. What's the first term going to be there? That's going to be -1. Okay, the second term, what's that going to be? 2. Third term, -3. And then the fourth term, +4. Okay, so it's just basically going -1 plus 2 minus 3 plus 4, forever like that. It's an alternating series is what you have on that. All right, so let's do the partial sums. This one is -1. Then we're going to do -1 plus 2, which is 1. Then we're going to do -1 plus 2 minus 3, and that's -2. And then you can take the previous term, -2, and then add the fourth term, 4, so that gives 2 like that. All right, you see the pattern? Yep, -1, 1, -2, 2, -3, 3, and so forth. And it's going to do that infinitely. It's not going to change. Okay, so what we want to kind of do on this is, well, think about whether that's going to converge or diverge. What do you think? That diverges. It's just going to get bigger forever. Okay, if you graphed that sequence, you would have two things. You would have one going up that way and one going down that way. So they're going to different directions like that. So basically what you do on this is you just say it diverges. You don't have to work anything out because you can see that thing diverges. Okay. All right. Any questions on that? Okay. So this section's not too bad. It'll give you a good introduction to sequence. These things are going to get a little bit more advanced as we go.